Good afternoon, class. Here's Chapter 3 Derivatives, Section 3.3, Basic Differentiation Formulas. And we have seen a big chunk of that. We are going to move on with the rest of it. Part 2. Exponential functions. Compute the derivative of the exponential function f of x equals a to the power of x using the definition of a derivative. F prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. So according to this formula, we get to the limit as h approaches 0. We have a fraction bar. F of x plus h is a to the power of x plus h. F of x plus h becomes a to the power of x plus h minus f of x, the same thing, a to the power of x over h. A to the power of x plus h, according to the exponential rules, is the same as a to the power of x times a to the power of h, and I write it in this fashion. So from the numerator, I can factor out a to the power of x, and I get the limit as h approaches 0 of a to the power of x times a to the power of h minus 1. Because the limit pertains to h, we can take out a to the power of x from the lim sign, becomes a to the power of x, the limit as h approaches 0 of a to the power of h minus 1 over h. And if you compare these two, you see that f of x is a to the power of x, f prime of x is the same thing times some multiplier, the limit of a to the power of h minus 1 over h as h approaches 0. This is some number. Now, here's a question. Is there an a, base a, such that this limit is equal to 1? Why are we looking for that? If that number exists, f of x becomes equal to f prime of x. If this limit becomes 1, if there is number a such that this limit is 1, f and f prime are equal. That is a fascinating discovery. So what they do numerical analysis, and they work with various numbers, including 2 and 3. And this portion, a to the power of h minus 1 over h, for number 2 becomes 2 to the power of h minus 1 over h. For number 3 becomes 3 to the power of h minus 1 over h. So and now h is approaching 0, so they start with 0.1 and then 0.01, 0.001, and 0.0001. They make it closer and closer to 0, and they evaluate each one. So when they evaluate the first one, when we let a be number 2, we call this f prime of 0 for a simple reason. If you replace the x with 0 here, class, f prime of 0, this becomes a to the power of 0, which is 1. So you're left with this part. And for 2, you're left with this one. And it's close to 0.7 or 0.69. We repeat the same thing for number 3. And that is f prime of 0 for number 3. And this limit is this one, or about 1.1. So what are we looking for? Is there an h such that this limit equals to 1? We found for number 2, the limit is let's say 7. And for number 3 is 1.1. So yes, there should be a number a such that a must be somewhere between 2 and 3. And that gives definition to an e. E is the number such that this limit, look at this one, we're going to change a to that number, which we call it e. The limit of e to the power of h minus 1 over h as h approaches 0 is 1. So this gives rise to the definition, precise definition of an e. E is such number. And as you know, nowadays, it's 2.71828, and it continues. indefinitely. What does it mean geometrically? Geometrically, this means that of all the possible exponential functions, y equals a to the power of x, the function f of x equals e to the power of x is the one whose tangent line at 0, v1 has a slope f prime of 0 that is exactly 1. First and foremost, remember when you draw exponential functions, a to the power of x, where a is larger than 1, it looks like that. And as a gets larger, the function gets closer and closer to the y-axis. That's why e to the power of x is somewhere between 2 to the power of x and 3 to the power of x. For e to the power of x, when you find the slope of a tangent line at the y-intercept, that must be 1. And here's the reasoning. F of x is a to the power of x. F prime of x is a to the power of x. The limit of a to the power of h minus 1 over h as h approaches 0. If we replace the x with 0, this becomes f prime of 0. This becomes 1. Class a to the power of 0 is 1. And this limit remains. And so f prime of x in general would be this piece, which is f prime of 0 times a to the power of x. And that one represents the slope of a tangent line at y-intercept. So this definition was given to you from algebra, and we went over that before. E equals the limit of 1 plus 1 over n to the power of n as n approaches infinity, or the limit of 1 plus h to the power of 1 over h as h approaches 0, which ends up being 2.71828, and it continues indefinitely, everybody. And here's the definition we just went over and proved it. E is the number such that this limit equals 1, the limit as h approaches 0 of e to the power of h minus 1 over h. What should we know? If e to the power of x is given, its derivative is also e to the power of x. That's all we are concerned with. No more, no less. We want to differentiate, and we want to find f prime and double f double prime, where f of x is e to the power of x minus x. So let's discuss that f double prime by looking at higher order derivatives of f of x. The derivative of a function y equals f of x is itself a function. Y prime equals f prime of x. Therefore, you can take the derivative of f prime of x, referred to as the second derivative of f of x. F double prime of x, or f, looks like a power, but it's not, in a parenthesis 2 of x. This differentiation process can be continued to find the third, fourth, and successive derivatives of f of x, known as higher order derivatives of f of x. Using the prime notation for derivatives would eventually become somewhat chaotic. We use the numerical notation f, and looks like a power, n in a parentheses, x, to denote the nth derivative of f of x. So f prime, f double prime, the next one f triple prime, but more than that becomes awkward. So what is f prime according to the formula that we should know? E to the power of x, the answer is itself, and minus x is minus 1. We are done with f prime. As far as f double prime is concerned, the derivative of e to the power of x is itself. Minus 1 is a constant, gives you 0. So e to the power of x, and we are done. Y equals sine t plus pi cosine t. We want to differentiate this. The derivative of sine is cosine, so this gives you cosine t. Plus pi is a number. Pi times cosine t, the derivative is negative sine. Therefore, plus pi times negative sine t. which makes it cosine t minus pi sine t. We want to differentiate this. H of t is the fourth root of t minus 4 e to the power of t minus cosine t over 2. So we have to change this so that power rule can be used, t to the power of 1/4. This one, you don't have to change it, but I just want you to see that this is the same as saying minus 1/2 cosine t. So if I'm differentiating, this one becomes 1/4 t to the power of 1/4 minus 1. This is itself minus 4 e to the power of t. This one is minus 1/2 cosine gives you negative sign, so makes it positive 1/2 sine t. This is negative 3/4 and makes this one 1/4 t to the power of positive 3/4, and we rewrite it as a root 1/4 the fourth root of t cubed minus 4 e to the power of t plus sine t over 2. You can keep it in this format. This is the same format we received. It's absolutely fine if you write it either way. It's up to you. Here's the example we have seen before. The distance in meters of an object from a starting point is given by s of t equals 2t squared minus 5t plus 4d, where t is time in seconds. What is the velocity of the object from 2 to 4 seconds? And as you recall, it simply becomes s of 4 minus s of 2, which is the total distance, over 4 minus 2, which is the total time. That's the average velocity, because 2 points in time is given. So you plug in 4, you plug in 2, you evaluate it. We've done this before. So we get 52 minus 38 over 2, or 7 meters per second. That's the average velocity from 2 to 4 seconds. 2 points in time given, meaning average. What is the instantaneous velocity and acceleration of the object? What is the velocity and acceleration of the object after 6 seconds? Velocity we had done. We took the derivative, but the long way by definition. Now we are going to find s prime of t or v of t, the easy way out, which is 4t minus 5 using the power rule. After 6 seconds, if you replace this with 6, 4 times 6 minus 5 makes it 19 meters per second. So that's really nothing brand new. Acceleration is the second derivative of the position function. So a of t is v prime of t equals s double prime. So if I differentiate this again, I get to the answer. When I differentiate it, I get 4. Now 4 is a constant. It's independent of the variable t. Therefore, the acceleration is always 4 regardless of the time. Any time makes no difference, 6 seconds, 10 seconds, 2 seconds. But the units are meters per square second. Why is that? A of t by definition is dv dt, the change in velocity, which has a unit of meters per second, and the change in time, which has the units of seconds, and therefore this gives rise to the units of accelerations meters per square second. When does the object reach a velocity of 31 meters per second? Set this to equal. Move the 5. 36 divided by 4, 9 seconds, everybody.